if you want to maintain a certain current, so you have to go to your control panel and say, I want a certain current, and then I apply a bias of 0.1 volt, okay? What will happen? 0.1 volt, in order to keep this 0.1 volt, there's a certain electron density in here, right? The tip has to contour, has to move around like the red curve, contour the surface like this, okay? If I apply 0.5 volt, right, keeping the same current, what I got is that I have nothing. I may hit a density where I see no current, right? So I saw a gap in your electronic structure of the surface. So you just a flat line like this. And finally, if you apply a voltage that's 1.5 volt, for the surface atom, this shaded one, you may have nothing, but then when you hit two foreign atoms, right? Let's say they are dirt or something, just because of the nature of these electronic state, you may hit at 1.5. You may hit the electronic state of this dirt atom, and you actually did pick up some electron density. And so you can see, right, by changing your bias, you're sampling across, right, your electronic state, sampling across the electronic state of your surface, and you're cutting, slicing a different electronic state, and measuring where they are from this. And this is the corresponding image that you see from the contrast. You can scan, the whole surface in raster across, and you can see they could be quite different, and they could probe empty envelope or fill envelope this way. Okay, so the bias potential may distort. One of the problems is the bias potential may distort what you see. So you always have to be aware of potential artifacts, and the key point, the local density may not correspond to the real atomic position. Right? Usually it doesn't, unless you're probing isolated, localized electron density at the nuclear. Okay, so here we have then we have to make a cautionary remark that the topography in STM give information on the local electron density state. So key point, it gives psi square, right? Psi square of the electron wave function. So this corresponds not your nuclear wave function. So it's the local electron density state, okay? And not the position of surface atom, unlike Reed or Saxet for that matter. Because Reed and Saxet, why they give you that? Well, because they assume a nuclear position to construct the model of your surface and then perform your scattering calculation on those. That's why it gives you the nuclear position, right? But here, the inherent image of the STM does not give you that. Now, if you work with STM for a while, and we have, you realize that STM is not really that powerful. Initially, it was a lot of fun. You can see all this tunneling of a single molecule and so forth. But that's as far as it goes, right? Because the limitation of the STM is that because you're talking about electron tunneling, so you have a little dirt on your surface, you cannot tell whether you have dirt or not, right? So for example, let me look at this image that my student collected. So I got this nice, beautiful image of my 7x7 surface, right? And I noticed that these dark areas, right? These dark areas must correspond to some foreign thing falling onto the surface, right? So, and I have no way of telling, right? For example, I have no way of telling this dark, what is the chemical nature of this dark area versus this one, for example. Is this oxide, or is it some nitrogen or some water molecule, or is it hydrogen that I have? I have no way of telling this, right? Because you just have you are all measuring electron, so they all emit electron or lack of electron. In this case, I'm probing empty state. So it's not chemical specific for lead, right? For STM. So that's a major limitation in STM. The second limitation, as you may gather from this, right, is that, okay, if I want to look at a well-ordered surface, this is a silicon 7x7 surface, I can see this individual atom, that's great, right? I can have a surface grid as my reference. But in most material science, you don't study such a clean surface, right? You may have a very heavily populated surface. You may have a saturated surface. At that point, you have lost complete reference, right? Here I have a nice, beautiful 7x7 grid, and then if I put a very, very tiny amount, a few molecules at a time onto this, and find those few molecules, I know exactly where they go, and that's great because I can do surface-specific chemistry on those. But if I want to go to the real world, you can't, because you cannot really study really high exposure on an STM surface, because if you have high exposure on an STM surface, you lost the surface registry, right? You have no idea where you are, because dirt looks just the same as your target molecule, and then it becomes a big mess. And then that kind of image is totally useless, because you have no registry to the surface grid that you got. Okay, so that's the limitation, right? So far people recognize that, you know, you can, it's fun to look at very well-constructed surface with STM, and you can do good physics with it. But that's about as far as it goes, because its own application is difficult to use it in chemistry. I mean, to do material science or even nanoscience with this is not so easy. Okay? And furthermore, right, let's say you are building a nano object with this STM microscope. You're talking about atomic spacing here, right? You're talking about atoms, right? Once you build this thing, how do you find it? Where do you find it again? You have no tool that you can relocate. Let's say I build a little atomic structure on this leg, right? This little triangle that I have here. Once I take my sample out, I have no way of finding this again, right? Because this is atomic resolution. It's vast, right? You have no way of finding your device again if you build a device on here. So there's a lot of technical issues associated with it. One of which, as I've tried to point out here, is that it's not chemical specific, and that really is a problem for STM imaging. Well, you may say neither is LEAD, but LEAD is chemical specific to a certain extent. Why? Well, because the absorbate has a weaker intensity compared to the substrate, because you have two grid, right? You have two patterns. One is more intense than the other, and the more intense one is always the substrate one, and the less intense one is your RDU's absorbate. So even though you are still studying simple system, you can say which one is absorbate, which one is not. Okay, so you can find more information about this review by an IBM guy at Yorktown in New York State. So Average Speedway, a very nice article in the early days. It's still a classic in terms of from the chemistry perspective.